There we go. So we have a record of today's event. All right, let's get started. The announcements this week are the same as 2 weeks ago. The first one is that the Rubin Users Committee is now stood up and it now exists. And so if you want to read more about what the Users Committee will do and who will be on that committee, you can look at the announcement at ls.sc/CLO6365. There's also a webpage for the Users Committee that has little bios for each of the Users Committee members and says what this committee is charged with at lsst.org/scientists/users committee. The first meeting of the Users Committee will be on Thursday, April 14th, and it's at 8 a.m. Pacific time. It says PST there, but we're on daylight time now, so it'd be daylight time. And these meetings of the Rubin Users Committee, the committee comes together to discuss various aspects of the Rubin Science platform and its usability and how well it's serving the users, but all are welcome to join in and listen as the Users Committee discusses these things. So that is open for you to do. And just the end part might be closed. So if you do show up to sort of listen in onto what the committee is discussing and maybe ask a couple questions, you might be asked to leave for the last 15 minutes while they have a closed session, but otherwise it's open for people to drop in and listen to. So Rubin Users Committee was the first announcement. The second announcement is that the application form for DP0.2, it's phase 2 of Data Preview 0, is open. Nobody who currently has an account with the Rubin Science platform or who is currently a delegate needs to reapply for phase 2. Everybody sort of automatically, you just keep your accounts and we keep going with Data Preview 0. But you might want to appoint your friends, colleagues, and students at the announcement in order for them to join Data Preview 0 as well and to get one of the 300 new accounts that will be available for DP 0.2. You can find the announcement there and all the instructions and the link to the form, application form at ls.sc/CLO6362. Just going to pause for a second and see if there are any questions about these two announcements. You can unmute or put your question in the chat. Okay, in that case, let's go on to our delegate profiles for today. I can see that there are 2. So I'll show the slides for you and you can unmute and speak to your slide and introduce yourself.
Hello, my name is José Costa Pulido. I'm working at the Instituto de Astrofísica de Canarias. And as a senior astronomer, I have a sort of permanent position. My science interests are mainly related to AGN variability studies. I usually work with light curve from blazars. We take our data from the observatory here at Canary Island, and we look also at changing look AGNs. And for the DP0 interest, I want to learn how to deal with light curve from selected target, to learn how to detect and characterize transient event of flares in light curve, and also to how to use a stack image to measure the morphology of our target in order to determine the ratio using the scaling relationship. So that's all. Thank you.
Great. Thank you, Jose, very much. Welcome. And next today with Christian.
Hello, my name is Christian Aganze. I'm a graduate student at the University of California in San Diego. And my science interests are in brown dwarfs. And so I work on trying to use brown dwarfs as tracers of the structure of the galaxy, so galactic archaeology. So I'm interested in simulating how many of them the Rubin Observatory will observe and what will be their colors and their properties. But as a scientific interest is simulating stellar streams, but not with Rubin, but with Roman. But that's also another science interest of mine. For DP0, I'm interested in again, we have part of an LSS grant, Kickstarter grant, and I'm interested in simulating brown dwarfs in DP0 and DP02. We're simulating them because they're already in there, but our proposal was to redo that. And then I'm also interested in learning how to use the math catalog, not catalog, but the frameworks, the matrix analysis framework. And I want to also see if I can find the truth tables that were inputs for DP0. So that's roughly my interest in DP0.
Excellent. Thank you. Thanks, Christian. Thanks for being here today. And thank you both for doing delegate profiles and for participating in Data Preview 0. So to go back to our agenda, we will now move into a presentation from Sylvie on photoses. And then once the presentation is done, we will come back and we will create our breakout rooms and proceed with the breakout section of this session. So Sylvie, I'm going to stop sharing and I'll let you share the slide deck and for your own, even though all the slides are in the same spot. I'll let you share. Hey, there you are.
So let me try to share the right screen.
And Sylvie, maybe before you start, can you give us sort of a time estimate, or is this like a full hour-long tutorial, or are you doing sort of like a 30-minute demo, or what's your plan?
Oh, please stop me. I think we won't do everything. It's so. Kurt said to me at 10. Please stop. We go in the breaking room. Tell it to me, because it's not possible to do everything. So,
okay, you're planning a pretty full tutorial, and I'll stop you if we get to 10.
Yes. So you see, but I want a slide deck. Okay, this is a slide deck. Okay,
And,
if I do this, okay.
We can see, should we also be opening our, is this mostly a demo, or is it going to be like a work along? Should we all?
No, it will be a demo. So I start by introducing the subject with the slides, and then we move to the demo.
Okay, so there'll be a
so
time.
I have two slides of introducing the subject, and then you will be able, following the slides on my explanation, then you go to the Rubin, and you can try to connect also now to the Rubin if you want to start. Okay, sorry, I cannot move. Why? Yes, I can move here. So you can start to go to the Science Rubin platform here. Try to have the maximum of CPU. I don't know if it is possible. And then I will return and I will comment what you have to do. Okay?
Okay, so people should log into the Rubin Science platform.
Yes. While I am speaking, please try to connect and choose, if you can, for CPU. So the goal is to make a demo to show how to use scikit-learn, machine learning Python package for photosite estimators. So the idea is to extract a set of galaxies with a magnitude distribution with a selection of those objects. And the point is that there is no time to comment a lot about how these objects are extracted. So I will skip it, but you will have it in the notebook. If you uncomment, you would be able to have these histograms. So from this magnitude, you know that you can build the colors, that is the difference between two nearby bands. And you have, with respect of the redshift, this feature for U minus G, G minus R minus I minus Z, and Z minus Y versus the redshift. And what you see is this kind of feature with a maximum here. If you take, for example, the humanus G, you have a maximum here at 0 redshift, and as the redshift is of the galaxy is changing here, increasing, this maximum shift here in the G minus R, you start to see this, and then you see this point here, up to this, just this point here. The point is that what you're observing is a Balmer, here, the break, and you can follow here the Balmer break in LSST filter up to under redshift equal to 1.4. And then between 1.4 and 2.5, you have nothing. And then the Lyman break enter late at redshift above 2.5. So the goal will be to use these and to build a typical plot Z-FOT versus Z-spec with some analysis of some values, the performance of the estimators. What we will do is we will compare 3 kinds of photo Z estimators illustrated here, and we will compare it with CMNN estimator that Melissa has proposed and that you can find in the contribution notebooks. And for the break, next session, during the breakup room, for the photo Z part, what I propose is to continue on the optimization of the hyperparameters of those photo Z. We will see validation curve, learning curves, cross-validation, research, and on. So, of course, we will only follow one estimator with all these features. So now, I hope you were able to connect to the RSP, and you have to, I hope you have the delegate contribution from GitHub. Otherwise, you have to do git clone this. Okay, and now I go to the platform. So here you have the delegate contribution directory. So I have to wait for your return to know that you were able to open so the RSP, and that you have in some working directories the delegate contribution DP0.1 cloned. On
my Jupyter lab is still opening, so probably others are having delays as well.
Can you see my screen of RSP?
Oh yeah, I can see your screen,
Okay.
but I tried to open up data.lsst.cloud and it's still, my Jupyter lab is still not started up, so I can't follow along yet. So we should probably just wait maybe 5 minutes.
Yes,
until
I wait.
until people start reporting that your instance of the Rubin Science platform opened okay, and you can open the notebook.
This is Adam, and I am in. It was a little slow to start, but seems fine now.
Okay, good. Mine is still loading, but it's probably just because a bunch of us just started to start up a 4 CPU session. Anyone else reporting they were able to log in fine and they're in the Rubin Science platform? Bob's got a thumbs up. Thank you. Julia's got some, oh, and Alan. Okay, so we're getting some thumbs up. I'm almost there as well. I'm just going to make sure I refresh my repository. And anyone doing a git clone right now will have an extra step. So we'll wait for a couple more thumbs ups. Okay, I have now managed to log all the way in and open up part 1 of your notebook.
Okay, so you go in Photo Z. In Photo Z, you have the CMNN estimator, and you have also this SCI kit learn estimator. You go, and you have the two notebook. And for the moment, we will look at the part 1. If I can start, let me know.
Yeah, I think we had enough thumbs up and mine even seem a little delayed. Oh, does anyone remember how to get the access to the terminal in order to do a git pull? I'm currently logged in, but my notebooks are not updated. Yes.
So if you have this kind of thing, I recommend to rename your repository on git clone again.
The question is, how do you open a terminal? How do you open a terminal?
Yes,
in Git?
yes.
That is actually the question. Yeah. Thanks, Adam. Yeah, okay, thank you. Okay, that should work. And for anyone else listening who may have missed it, I did put a link to today's slides in the chat, which had that single slide page of instructions of how to git clone and stuff, in case you didn't do a screen grab at the start there. Okay. Okay, sounds like no more questions, so everyone is at least on their way.
Yes, of course. I forgot to say something. Okay. Because we are going to make a query, I have stored in a file. So I will do interactively. So I make new terminal. And you go in Scratch. And you see a number of directories, but perhaps your directories, home directories, or your user directory, sorry, is not there. So if it is not there, you don't find your name, you ask, who am I? And you create that directory of this name.
Oh, you didn't, so the notebook won't create that directory for people?
Yes, it will create, but the point is you will have to make the query. It's just to bypass the query to go faster. But if you want to, to make the query, it's up to you, it's optional. The point is that, so let me show you in LSST and in Photo Z part 1, you have this file. So you have the possibility of creating this hierarchy of directories, your username in Scratch, and photo Z part 1, and you with this file, and it will be fast when we will do your query because it will read this file. But if you prefer to do your own query, there is no problem. It depends how fast the server will provide you the data. So,
For doing our own query, how long should it take?
In fact, we can manage to reduce the number of the query is done on in a region of the sky of 1 degree radius. If it is too slow, you can reduce the radius and it would go faster. So it is not necessary to ask the 1 degree. I am using the 1 degree, but so I start.
Okay, yeah, I'm just gonna put those instructions that you just said. I'll put them in the chat in case anyone missed them.
Sorry. Okay, so what I do, so we start, so you start with a number of imports. Okay, those imports has already been presented previously. Not all are necessary, but I have not made some cleaning. To make the plots, I will lose all of you because it's nice. We can zoom on part of plots. So okay, so I execute step by step. Okay. So there are some utility functions. We won't need them because it is to discuss about the selection of the sample. And I have proposed to skip this part because it's possible that I would not have not enough time to introduce scikit-learn estimation. So, okay. Here, in configuration initialization, I have some parameters to define the size of the plots that you will see. So you can execute them. Or perhaps I start with a high number. Perhaps I should. I restart my kernel to be sure to start at cell 1.
Oh, so you restarted, but if we started from cell 1 just now, we don't need
yes,
to.
It's to have the same same number as you. Okay. So okay, so so 1. Okay. And then so utility function. Okay, now you have defined the parameters for the plots. We are at the part where we configure the path. So if you want to read the file directly from the disk, okay, it is set up to read the file if you have it. If you don't have it, you will make the query to the database. Here there is some flags. They are set that if you make a mistake, your query will be saved on the disk and you won't ask again the database for your data. So I define here the 5 sigma magnitude cutoff. We will need it then for the query. And now I build the query to the database. In this function, you pass here as in C the center of your region. You ask for a circle around this center, and here this is the radius of the query, and you see your query, typical query that you have seen in the past, requesting the magnitude of the object in the database, their error. So you have two tables, I remind you. You have the DC2 object table, and you have the truth table. Those two tables are joined together. Here you request your region with these parameters you have passed. And what I have added is a cut on the magnitude, because in the database there are objects with magnitude that will not be visible in the telescope. So I propose to make a wide cut with the threshold plus 5 sigma in the database. Okay, so once you call the service to access to the database here, you specify your region and the radius here. The size I have chosen 1 degree. If you want to go faster, perhaps try 0.5 degrees. Now you call the function, oh, sorry. So, and you see the query. Here I specify the file name. Either you will read the result of your query from the file name, or you will store the result of your query in this file name, not to start again your query. Here, I put 2 files flags that show the plot I have shown you during the introduction on the slide. So we skip this part. You would be able to return later to this. So on here, there is a series of, okay, so now, okay, you start and you read your data, you ask to the database. So it's the same way as introduced before in previous notebooks, previous session. So you do this and you have to wait. For me, it's very fast because I read the input file is found. The file is found in my Scratch directory, so I read it. For you, perhaps you have to wait. And at the end, when you get all your the result of your query, so you get them here in a Panda table. And this Panda table will be written in your directory. You don't have to worry about the creation of your directory. It has been done previously in the notebook. And once you have your query, you can see your table with your results. So let me know when you have your result. If it is too long, you kill your kernel and you reduce the size of the radius.
I had run this before, so I had the file already.
Yes.
Maybe if someone is doing the query live, you can let us know how it's going. Okay, so for Adam, it was about 3 minutes, but it sounds like, Adam, you did it and it finished already in 3 minutes, so that's good. Oh, I had to reload my whole notebook page, so I'm a little behind. Just gonna catch up. While we wait for anyone else who has questions or encountered an issue. Go ahead and unmute and ask questions or post in the chat if anything came up for you as you were making your way up to, where are you now, Sylvie? Which cell should people be in?
So you should be at the table SQL result head.
Okay.
So it's so around 30 because I have executed additional cell. It's at the end of the query.
Okay, will you get that table written out of the query result? Okay. Okay, I've made my way back to that point.
Okay, so we continue. So I put this table into data. Okay, and first things, I reduce the size of the names in the tables. So I rename here below the columns of my table. Oh, of course, here I can check if I have written my file in my directory. So it is here. So it's just to remember how to change the values by mapping on the Panda table to change the number K1 into Galaxy, just to remember how we do this. And then I drop all the objects that are not galaxies. I drop also NA if there are some. On here, there is almost now 1 million entries. You may have less if you have reduced the size.
Sylvie, the step where you get rid of not galaxies should have been not necessary because your query had truth type equals 1.
Perhaps. Yes, it's possible. Yes.
That's it's fine because
yes.
dropping them, you just probably didn't drop many.
Just to remember to.
Yeah, so it didn't
the
hurt.
commands.
Yeah, unnecessary, I think.
And in this table, I just add the colors because the colors can be used to make some plots just to study the input. And then we are making some plots, but as I have said, we won't. I won't comment this part now. Only if there are some questions for the breakout session. So you can start to execute all these commands, and because there are these flags, they are not executed. So you go up to machine learning, start here. So in the desk, in the LSST science book, there are some requirements about
Can I ask, you just executed like a whole bunch of cells. Could we just skip them without executing them, or do we have to execute them?
We don't have to execute them.
Okay, because just my machine is just running so slow that even scrolling is like painful. So I could just scroll down to machine.
So for me also it is slow. I don't know why.
Okay, so I could just scroll down and not execute anything, and it would be okay.
So I think it is very slow because okay, I'm just stuck here. The idea in this is to go from what you have in the catalog is average. What I understand, we have average magnitude, and we have errors on this magnitude. in real life, we would have randomized flux or magnitude using these errors. But what I propose here is to take the average. And in that things, what we make is we randomize, we apply cuts for the photo detection limits on randomized, and then we cut, and we continue to work on magnitude, average magnitude. So it's false that you don't have to execute them. For example, here you have to do this. We compute some magnitude that would be detected.
Okay, so under apply photometric
you apply, you have you randomize your magnitude.
Oh,
that is now called the magnitude you detected by calling this. So this you need. And somewhere I cut here, I apply a photo detection selection cut on detected magnitude.
Okay, I'm just going to execute all of the cells down to.
Yes. And so you add a column detected for the galaxies that you would detect in your detectors. And then you drop all the non-detected. And all these plots are to check that, okay, we keep the good. That way it was long. So here, but we will see later. So we have reduced the number of galaxy sample, and we are around 30,000, if I remember. So while you are continuing executing the both cells, so the requirements of the science book are the following. So we have limited in magnitude. In R, we could request even more stringent cuts on magnitude from some physics. So the performance on photo Z is usually written in terms of sigma Z divided by 1 plus Z. And this sigma Z should be smaller than 0.05 with a goal of 0.02. We request also the fraction of 3 sigma of outlier should be less than 10%. We should have also a very small bias defined as follow on the uncertainties. There are also, so it must be similar, the uncertainty sigma Z divided by 1 plus Z should be similar to this. There are some other definitions that are not using this division by 1 plus Z. Okay. So what I am following here is some notebook which was introduced by Jeff Newman during a dark energy school, desk dark energy school in 2016. And I draw, as it was done, some lines. So just I am preparing some lines. Here you have what the photo Z relation should follow. And the dashed line correspond to defined region with outliers. So I execute this. I am preparing a function that was defined in the Jeff Newman notebook, defining some quantities. The quantities, the standard deviation defined like this. divided by 1 plus Z spec. The median absolute deviation defined as like this. And there is also a definition of the outliers to compute the fraction of point estimations that are above or below the dashed line we have seen, and also a way to calculate the bias. And we prepare a string to show in plots the performance. So here you have also a function that I have taken copy the notebook of Melissa defining the CMNN estimator. So just for comparison, I have copied it. If Melissa, you want to comment, you can comment it perhaps later when we will execute it. So we start the machine learning here. So from the data, we extract the target by selecting the redshift column, and we extract the feature here with the magnitude, the 6 magnitudes. It's the first try. We could add more columns if we want. This will be, you can play later with this. So what you have around a total of 36,000 samples. Because the training takes time, I forced to use here, for example, 10,000 samples for training. I define the number of remaining samples for the test. And I call the scikit-learn train test split to split the original sample into samples. Then you have the feature training, the test, the feature test sample on the target train and test, calling for this. And you can check, just an illustration, you can check the size. So you have your 10,000 sample in your X-train, and you have the remaining sample in your test. Now I define the regressors we are going to see. So I must go quickly. I think I will have time perhaps to only 1 or 2. So the regressor, I start by a linear model. And the point is that I wanted to show how to pipeline series of tasks inside scikit-learn. First, you have your feature, and you augment your feature by using polynomial features. That means you will introduce the power of your features, including, I think, cross term. And when you use a linear regressor, usually you should always normalize your input features, so you call the standard scalar. And here, you should also regularize your linear estimator with a regularization parameter. I put here a small parameter, alpha. Okay, so you do this. Then I define the random regressor, forest regressor. And here I am using the parameters that were defined during the Jeff Newman presentation. So here I don't try to play. And now here I introduce a kind of promising regressor, which is proposed by the team from INRIA, which have an excellent MOOC I have just followed the previous week. So, okay, you did this regressor, now you will compare. In scikit-learn, you have a set of evaluation metrics that are slightly different from the one, the metrics I have introduced, especially dedicated for PhotoZ, but we can also have them. And I introduce some cross-validation because from your sample, you can, training sample, you can extract subsample randomly And from this bootstrap sample, you can fit different models. And it is useful, for example, if you want to make not only a point estimate, but you want a distribution on your output photo Z. So this is an example of doing so. You specify that you will have 5 bootstrap samples and that you shuffle your galaxy sample inside these samples. And what you do is you call cross-validate with your regressor you have defined. Here we have the rich regressor. We introduce the X train, Y train, and we pass here the evaluation matrix we are interested in. And we ask also to return the estimators, so you do this. And the output of your scikit-learn cross-validation comes into a dictionary, Python dictionary. You can transform this Python dictionary in a Panda data table in which you can see the results. So what you see is your 5 bootstrap sample. On each one, you have fitted a model. And here you have in this table the result of your evaluation matrix, the R2 matrix, the mean absolute error on the, this is the result on the test. So, and also this is the mean square error. You take any of these estimators. For example, you take the estimator 0. So you take your estimator from the Python dictionary and you predict on your X-test feature test the predictions here. So for this estimator, it goes very quickly. And then you plot, you are going to plot the result calling this function. So you see the result of your estimator, rich estimator. So what you see, you use the data shader. And you superimpose the plot lines. And you see here the estimation. For example, here, your mean absolute deviation is about 0.09. And your bias is null, okay. But you have a huge amount of outliers. So the interest is that you can now zoom on some region with your data shader. I don't know if you can move, you can, okay, you can play with this. So now you can call here the performance metric, which is written in your CV result. And you can print this. So you have this R2 score. The R2 score, you can think about a kind of correlation coefficient squared between the estimated values for each Z spec and the Z fault. Yes. Or it's a kind of correlation coefficient. The point is that your R2 score means you have it is good when it is close to 1 and bad when it is close to 0. So it is not an excellent estimator. And here you have, I have taken the square root of the mean square error. Now, if you try the random forest, this time I am reducing the number of samples I provide, and I am not doing cross-validation because it would be too slow. So what I just do is a new trend test split. And in the X-train, now I will have only 8,000 samples. So let's execute this.
Sorry, Sylvie, before we move on, you use this R2 score and MAE something, where, and then I was scrolling back up to see, where do people learn more about what these are? Are there links somewhere to?
Yes, so I should have added Wikipedia. In Wikipedia, you can find the definition of your R2 score. I think it is much better explained than in scikit-learn.
Okay, so these are things that have come out of scikit-learn.
It's not special to, it's a definition in statistics.
Okay.
It's R2 score. And I have looked before the presentation here on, okay, there is a very nice article in Wikipedia. On
Okay, so these ones are standard because the other one,
they are different from the one here, written, computed, especially with regard of photo Z or photo Z interest.
Yeah, those ones came from a module that you defined. So anyone using this notebook can go look and see exactly what MAD is.
Yes, so these are defined in here in this get stat. So it is specially for photo Z estimation. And you are the written definition, and you can see how it is computed. Mainly the difference comes from the division by the 1 plus Z almost everywhere, following deviation from the main line.
Yeah, okay, thanks. Yeah, I knew people could get more information on those statistics. I was just wondering where people find out what these other statistics were, but okay, it's on Wikipedia. Okay, thanks, Sylvie.
So now we can try random forest. So as I said, now you have I choose 8,000 events. I don't do cross-validation. I don't try several models because it takes some time for the demo, but you can try cross-validation. What you do, so you fit your model, and then you estimate on your test sample, and you compute your statistics, and we will do the plots. And what you see is that this relation is more straight than the previous one. You have a kind of S shape here with this linear model, even if you add non-linearities by adding polynomials. Here it is straight. This MAD matrix is much better, and you have much less outliers outside these lines. And again, you can use the scikit-learn. So here you have 0.65, which is better than what you had, 0.49. For example, of course, your errors are also better. 0.246 compared to this 0.355. So your random forest regressor looks better if I have time, or so now perhaps I will try to run selected cell on all below. So I try this histogram gradient boosting regressor, which is another model based on decision trees, which has another philosophy that I don't have time to explain. But we will have a look. So this regression kind of regressor is proposed in the MOOC I have followed. And what you see here, you see again this strange shape on this regressor. So it is not probably optimal. There are perhaps some tuning to do on its hyperparameters. So you have a very bad R2 score. But your root mean square error squared is not that big. And now we are running the CMNN estimator.
It's 10 exactly now, so that might be a good place to stop and do the rest in a breakout room. Yeah. Okay, cool. So that gave people 3 different demos of 3 different photos, the estimators, and how to compare their results. So thank you, Sylvie, for that so far. Round of applause for Sylvie, please. Thank you, everybody. And then, so in the breakout room, looks like we got pretty close to the end of this notebook. So in the PhotoZ breakout room, can continue with this notebook and then do the part 2 notebook as well. Is that kind of your plan?
Okay.
Yeah. And we can do comments or questions that may have arisen while we're working through that notebook now. We don't have to go immediately to the breakouts. Been kind of following some of the questions that came up in the chat, but most of them are getting resolved. So any questions for Sylvie before we do breakouts?
Question and a comment. The comment was I ran on just a single small instance. I didn't do the query, but I did everything else and it was perfectly fine. It was going as fast as you were. So you might not need the big instance. And then the question was, I actually got down to the where you asked the question of whether you should normalize by 1 + c, but the plots didn't tell me the answer. So I wondered if you had a conclusion there.
So the point is that the normalization that in what result I am following what Chef Newman did, and I think it is usually done in the community for PhotoZ. So because we expect that at high redshift the performance becomes bad. So. But we expect that the performance or the scatter and increase like a constant times 1%.
Yeah, no, I mean, that's the standard practice. I just didn't quite know what the plots were supposed to tell me about that. That's right.
Right, the plots don't have any divisions by 1 + z. It's only the statistics. So I think the plots don't tell you anything about whether or not you should divide by 1 + z in your stats.
Yeah, okay.
Yeah. Any other questions for Sylvie? Thank you, Henry. Okay, I'm going to share screen so that we can look at our breakout plan. All right, so we'll definitely, as always, have the main room here. For general questions. And we'll definitely have room number 1 for photo C, today's topic. And so from here, we can have any other rooms. If there are new people here who'd like to work together through an introductory level notebook, we can make a room for you to do that. If we have resolved stellar populations or large scale structure or variability people here today, we can make you a room. Let's put it in the chat.
My plan was to dive a little bit into the point spread functions and try to understand that data structure better and how to convolve and so on. So if anyone else is interested in that, I'm happy to collaborate. We can be the blind leading the blind, or maybe there's an expert.
Yeah, so looking at what aspects of PSFs?
Well, so, there's point spread functions that come along with the images. I sort of wanted to understand how to use them. That data structure is a little strange, right? You get a kernel, you have to go figure out where the point spread function image is. You can't just display the kernel with AFW image. You actually have to call a method and stuff. And I've gotten partway into that, but I wanted to get, further so I understand.
Okay. Interesting. So retrieving PSFs and using them. I will make a breakout room for that if anyone else indicates that they might go to it. Otherwise, that's a good thing to just work on in the main room.
Yeah, that's fine too.
Yeah. So I'll wait and see if anyone's interested in maybe seeing how to retrieve the PSF from an image and then how to work with it. Just waiting for anyone in the chat to say yes. Also, I'm going to stop recording now because we're going into